Hey guys, welcome back. In today's problem, we are given an integer array called nums, along with two integers k and dist. Our goal is to divide the array into k contiguous subarrays. Now, there are two important rules to remember. First, the cost of a subarray is simply the first element of that subarray. Second, there is a constraint on where the subarrays can start. If the second subarray starts at index I1 and the last subarray starts at index IC1, then the difference between these two starting indices must be less than or equal to dist. So we are not free to place subarrays anywhere. Their starting positions must stay within a limited window. The task is to minimize the total cost, which means we want the sum of the starting elements of all k subarrays to be as small as possible. The first subarray always starts at index 0, so its cost is fixed as nums of 0. The real challenge is choosing the starting points of the remaining k1 subarrays. Since the cost depends only on the first element, we want those starting elements to be as small as possible. However, we can only choose starting positions from a restricted range. All starting indices from the second subarray to the kth subarray must lie within a window of size dist. So this becomes a sliding window plus greedy selection problem. We slide a window of size dist plus 1. Inside that window, we want to pick the smallest k1 values. Add them to nums of 0 to get the minimum total cost. Example 1. Let's look at the first example. We are given the array of elements, with k equals 3 subarrays and dist equals 3. That means we must divide this array into 3 contiguous subarrays, and the difference between the starting index of the second subarray and the last subarray must be at most 3. One valid and optimal way to divide the array is: first subarray is 1 and 3. Second subarray is 2, 6 and 4. Third subarray is 2. Now let's calculate the cost. The cost of each subarray is its first element, so first subarray cost equals 1. Second subarray cost equals 2. Third subarray cost equals 2. Total cost equals 1 plus 2 plus 2 is equal to 5. Now check the distance rule. Second subarray starts at index 2. Third subarray starts at index 5. Difference equals 5, 2 is equal to 3, which is valid because it equals dist. So the minimum possible cost here is 5, and no other valid division gives a smaller cost. Example 2. Now let's move to the second example. The array is 10, 1, 2, 2, 2, 1, with k equals 4 and dist equals 3. We need 4 subarrays, so we need 4 starting points. The best valid division is 10, 1, 2, 2, 2, 1. Now calculate the cost. Costs are the first elements, 10, 1, 2, 2. Total cost equals 10 plus 1 plus 2 plus 2 is equal to 15. Check the distance rule. Second subarray starts at index 1. Fourth subarray starts at index 3. Difference equals 3, 1 is equal to 2, which is less than dist. So this division is valid. Another possible split might look tempting, but it violates the distance rule because the start indices become too far apart. Hence, the minimum achievable cost is 15. Example 3. Finally, let's look at example 3. The array is 10, 8, 18, 9, with k equals 3 and dist equals 1. Here the distance constraint is very strict. The best valid division is 10, 8, 18, 9. The costs are 10, 8, and 18. Total cost equals 10 plus 8 plus 18 is equal to 36. Check the distance condition. Second subarray starts at index 1. Third subarray starts at index 2. Difference equals 2, 1 is equal to 1, which matches dist. Any other split would push the starting indices too far apart and break the rule. So the minimum possible cost here is 36. Let's understand this problem step by step. We are given an array, and we need to divide it into k contiguous subarrays. The cost of each subarray is simply its first element. So naturally, we want those starting elements to be as small as possible. Now here's an important observation. The first subarray always starts at index 0. That means nums 0 is mandatory and will always be part of the answer. So the real challenge is choosing the remaining k1 starting points. But there's a constraint. The difference between the second subarray start and the last subarray start must be less than or equal to distance. That forces all remaining starting indices to lie inside a sliding window. To solve this efficiently, we slide a window across the array and dynamically track the smallest k or 1 values inside that window. We use 2 heaps. One heap to store the selected smallest elements. Another heap to store unused elements. Whenever the window moves. If an element goes out of range, we remove it. If a smaller element enters the window, we replace the largest selected element. At each valid position, we update the minimum possible cost. Finally, we add nums 0 to the result and return the answer. This approach allows us to handle large inputs efficiently. Alright, logic is in place. Let's hit run and verify with the sample inputs. Looks good. No edge case failures. Submitting the solution now. And boom, accepted. Efficient heap-based solution with sliding window constraints. If this explanation helped you understand advanced sliding window and heap optimization techniques, don't forget to like the video, subscribe to the channel, and check out the full solution link in the description. See you in the next problem.